Hi, welcome back to the channel. In today's lesson, we will see differentiation of polynomial functions. We will see how to differentiate polynomial functions both from first principle and with the formula using these two examples. That said, let's get into class. Our first example, I want us to use the first principle of differentiation such that we're saying that an increase in y will correspond with an increase in x. That an increase, let me just denote an increase in y equals an increase in x. So that y now plus a change in y will be equals to 4 into x plus a change in x all squared plus 7 into x plus a change in x minus 2. Now 2 is a constant, 2 does not have an x. So I'm not changing anything with respect to 2. Now so that, let me expand this. If I expand this will become y plus change in y will be the same thing as 4 into x plus x. Let's perform this here. X plus change in x into x plus a change in x. Obviously, this is the same thing as x into x plus a change in x plus change in x now into x plus a change in x. So that this is the same thing as x squared plus x change in x plus x delta x plus delta x, that's the change in x, all squared. We can now sum this up. This will be x squared plus 2x delta x plus delta x all squared. Now the bigger bracket. Now here will be 7 now into x plus delta x minus 2. Let's open the bracket. So this is y now plus change in y to be the same thing as 4x squared plus 8x delta x plus 4 delta x all squared plus 7x plus 7 delta x minus 2. Let's call this equation 2, while this is obviously our equation 1. Now, next thing is to subtract from our first principle. We're subtracting equation 1 from 2. In case you missed our introductory lesson on differentiation from first principles, please do not hesitate to use it. The description below will place a link to that lesson, and to ensure you get our lessons anytime we create them, kindly do us a favor by hitting the subscribe button. That way you'll be sure to get our lessons anytime we create them and you encourage us to do. I'm subtracting equation 1 now from 2. That will be y plus change in y delta y minus y. I'll be left with delta y to be equals to, here I have 4 squared. Obviously I have 4 squared here. This and this will give way, or rather, let me just show it here so that we'll see it vividly. This is 4x squared plus 8x delta x plus 4 delta x all squared plus 7x plus 7 delta x minus 2. Now this will be minus equation 1. That's the whole of 4x squared. To avoid me repeating brackets, let me just take it directly. That will be minus 4x squared. Now minus 7x, and also my minus 2 here will become plus 2. That's plus 2. Now look here, we have minus 4x squared and we have plus 4x squared. That gives away. We have minus 7x and we have plus 7x. That gives away. I have plus 2 and minus 2. So for my change in y, I'll be left with 8x delta x plus 4 delta x all squared plus 7 delta x. If you look at this closely, you see that I have delta y and I have delta x all around. So we can now divide through. We can divide through by delta x. So that I'll have delta y over delta x now equals to, if you divide 8x delta x by delta x, you'll be left with 8x plus 4 delta x, because I have 2 delta x here, this is delta x squared. If you divide one will go, then I'll have 4 delta x. I have 7 delta x divided by delta x, I'll be left with 7. Now let me call up a fresh page. Here's where we got to. So that as delta x now tends to 0, first principle, we know that my change in y over change in x will also tend to dy dx. So that obviously my dy dx will be the same thing as 8x. Delta x is tending to 0 times 4. The whole of this will become what? 0 plus 7. Now here we've seen differentiating this from first principle. Now let's use a formula. Our formula tells us that if I have y is equals to axn, my dy dx will be the same thing as a is the coefficient times n the power x now raised to power n minus 1. Now look at it, so that the equation is 4x squared plus 7x minus 2. Our equation is y is equals to 4x squared plus 7x minus 2. So that my dy dx obviously will be the same thing as 4, that's my e, into n is 2, x raised to power 2 minus 1, plus 7, n here is 1, into x raised to power 1 minus 1. Now, minus 2. Now, here when treating a constant, this is 2, and this as 2x raised to power 0. That's still 1. X raised to power 0 is 1. So that this will be 2 into 0, x raised to power 0 minus 1. Now, so that dy dx will be equals to 4 times 2, that's 8, x 2 minus 1 is 1, plus 7. 7 times 1 is 7. X raised to power 1 minus 1, that's 0. X raised to power 0 is 1. 1 times 7 is 7. And here, 2 times 0 is 0. So everything here becomes 0. So my dy dx obviously is equal to x plus 7. You can see, same thing we got from first principle. Now let's look at the second question. Here is a typical polynomial, and here's a typical polynomial function, and having this from first principle will be very tedious. So the best thing for us to use here is to derive from the formula. Remember, our formula says y is equals to ax raised to power n, then your dy dx will be the same thing as a n x raised to power n minus 1. If my y is equals to x raised to power 5, we will treat that for each item in the polynomial function. So that my dy dx for this function will be the same thing as, here my a is 1, that will be 1 into 5, x raised to power 5 minus 1, plus 4, that will be into 4, my n here is 4, x raised to power 4 minus 1, minus 3 into 1 again, x raised to power 3 minus 1, plus 3 now into 2, my n is 2, x raised to power 2 minus 1, minus 5 into 1, x raised to power 1 minus 1. Then lastly, we have plus 7. Remember, when you treat constant, this is as good as x raised to power 0. X raised to power 0 into x raised to power 0 minus 1. So that dy dx conclusively will be equals to 1 times 5, that's 5, x raised to power 4 plus 16 x raised to the power 3 minus 3 x raised to the power 2 plus 6x and minus 5 x raised to the power 0. Now plus 7, that's 7 times 0, obviously that's 0. So that dy dx is equals to 5x raised to the power 4 plus 16x raised to the power 3 minus 3x squared plus 6 minus 5. With this, I hope you understand how to perform differentiation of polynomial functions. Thank you for staying with us and see you in our next class.